Okay, so here we go. So last time we were talking about the fundamental theorem of calculus. Again, kind of a rewind. But the big idea is it's a fantastic sort of template on which to kind of compare, ideas that you're trying to digest about Green's theorem or the two-dimensional divergence theorem. Is just notice that anything that you understand about the fundamental theorem of calculus, there's kind of an analogous point of view to be had within Green's theorem or the divergence theorem. So, for example, we talked about how, even though, of course, when you compute accumulation is something that you compute or measure on the boundary, but it's perfectly visible that it's actually doing the actual changing in the interior, and you can see that specifically. And furthermore, that the integrand, the derivative in this case, is telling you explicitly where and how much, right? It is specific. Let me zoom. Here we go. It is specifically because that derivative, aka the integrand, aka the change density, because that is positive, that you can see that that's where change is actually happening, right? And then we made the sort of analogous observations about circulation in the context of Green's theorem. You can see, I like to think of little leaves floating in the water, right? And as they float down sort of the center line here, you can imagine they'd be kind of turning because they're being pushed harder on one side than the other. Whereas leaves floating over here, where the velocity is basically constant, they're not going to be turning particularly at all, and likewise down here. Right? So now I just want to, one last thing I want to point out along these lines is that the numerical version of this also works analogously. So here we have a specific example concerning the fundamental theorem of calculus and how to interpret the derivative. Is there more change in this function happening at the point 1 or at the point 2? Well, again, perfectly obvious from the picture. You can just see it changing more near 2. Visible, right? But the derivative, aka change density, you can plug into the derivative these 2 points, that you're trying to decide between, and then just look and see which one's bigger. And the fact that the derivative is bigger at 2, clearly bigger at x equals 2, that's the algebraic or arithmetic, no geometry required resolution of the question that, clearly more change is happening at 2 for algebraic reasons. Right. Okay, so I just want to point out that the same thing works with Green's operator for circulation as circulation density, and divergence concerning flux questions as that is flux density. So we've got, in this example here, we have some vector field. Oh, yeah. Sorry.
So is this like absolute dependent? Like if it was could it be like negative 28 and negative 22, and then would it just be lesser negative?
Depends on the way the question is phrased. If the question says where is the greatest change, greatest positive is greater than negative, right? But if it's, is there, I could imagine a different phrasing where it might be implied an absolute value. But it's really going to depend on the phrasing of the question. Yeah. It's a good concern. Yeah. Okay, so analogous here. Now again, don't get bogged down in what the vector field is. That's specifics. And but what we have here is we have a solid region and its corresponding boundary curve, and there's going to be some total amount of flux, and there's going to be some total amount of circulation, and what those totals are don't really matter for the purpose of the example. What we can say, though, is if I'm interested in comparing these 2 points, both inside of our rectangle, and I want to know where is there more circulation happening, right? I don't have to be able to draw a picture. I don't have to be able to visualize little leaves and how they're spinning or not spinning or what have you, right? I can just plug those into the appropriate density. And Green's operator is circulation density. If you want to understand how things are circulating, just plug those points into Green's operator. And again, see which one's bigger. All right, here you go. 28. 28 is greater than 22. That means there's more circulation happening at 2, 4 than there is at 3, 3. right? And then likewise, if you're interested in flux, there's a certain amount of total flux here, and that's, fine and all. But between these two different points, where is more of the flux coming from? Flux density tells us that. And again, simple calculation. You can just compute the divergence, aka flux density. And into that flux density, you just plug these same 2 points and see which one is greater, right? And 17 is greater than 13. So at 3,3, there is greater flux coming from that point, or happening at that point, or however you want to say it. Okay. All right. So I'm a huge fan of the analogy here with the fundamental theorem of calculus. The huge advantage being, of course, that we can see so much better what's happening and how, what do I mean by this idea of an accumulating quantity? And this corresponding result that even though we measure it on the boundary, it's actually happening in the interior. It's so visible and satisfying here. And then you can use that understanding that you gain and try to develop some analogous intuition and understanding about Green's theorem. Okay, so that finishes that. We're going to, I forgot to erase my mess from last class. Sorry about that. We're going to move on now to 6.3. Real quick, I want to talk about what a conservative vector field is. This is just terminology. Frankly, I'm not a big fan even of this terminology. A vector field is conservative if it's a gradient. And it's another one of those situations where I'm like, okay, well, why don't we just call it a gradient, right? Why do we need a whole other word for it? I think it's silly. Now, that said, there is a good physics reason for invoking the word conservative. And it has to do with conservation of energy. Which again is a physics thing. Right? But for math reasons, gradient I think is just more bluntly, communicative, right on the nose, obvious terminology. Okay. So be prepared to hear both of these words. Okay, that said, when you have a gradient field, if you are interested in computing a line integral of that gradient field, neat fact called the fundamental theorem of line integrals. You can compute a vector line integral of a gradient with what appears to be our familiar old formula from the fundamental theorem of calculus, f of b minus f of a. And as much as this looks like the fundamental theorem of calculus, they kind of copied the name accordingly. It's the fundamental theorem of line integrals. Okay. So hopefully at least believable by analogy. I mean, we don't have any mathematical reason to believe this yet, but it's not the biggest shock, hopefully, that we've ever seen. Okay. I do emphasize, though, very important, this is not just any old random line integral. There is a catch. As we've already discussed, this cannot just be any random line integral. The vector field has to be a gradient. If your vector field is not a gradient, then this theorem makes no comment at all about anything to do with that vector field. Okay. All right. So, how are we going to understand this thing? There's different takes that one can have, as y'all can probably suspect. I'm going to take an accumulation point of view. What I really like about the accumulation and density point of view on all these theorems, this is going to be like our fourth, I think, such theorem. Already. And we've got, let me think now, arguably 2, maybe 3, depending on how you look at it, more of these theorems to see. What I like about this point of view is that this unites all of them. All of these various theorems can be understood, I think, most succinct, most crisply by the fact that there's a quantity that's accumulating over interiors. Quantity computed on the boundary that's actually happening and accumulating over interiors. And that such an accumulation can be represented with an integral of an associated density. So this is the case for Green's theorem, as we first saw, the 2D divergence theorem, as we saw after that. And then for analogy purposes, I pointed out the fundamental theorem of calculus, same deal, right? And now, here's our fourth example. And it's going to be a lot of the same ideas. And I feel like the more times we go through these ideas, the more it'll sink in, perhaps. So here we go. Okay. The accumulating quantity in question is change, just like with the fundamental theorem of calculus. So, on the fundamental theorem of calculus, if you have some interval, and given an interval, change says how much does the function change over that interval? It's f of b minus f of a, right? So same thing here, and I'm going to make the claim that again this is an accumulating quantity. Specifically, it accumulates over curves. Now, this is a new statement. In the context of the fundamental theorem of calculus, we were looking at intervals on the x-axis, one-dimensional context. This is different. These are now curves in space, or in the plane at least. So I claim, though, accumulation in the sense that however much my function f, whatever that is, however much it changes over that purple curve, that's going to equal to how much it changes over this first green segment plus how much it changes over this second blue segment. And just for intuition purposes, I like to think, again, as I have written here, driving along a mountain road, right? And, okay, how much does my altitude change as I drive along the road? Well, look, over the green portion of the drive, if I gain 100 feet of altitude, and then if over the blue portion of the drive, if I gain 200 feet of altitude, well, 100 on the first part, 200 on the second part. Grand total, I gained 300 feet, right? And so over this entire purple curve, of course, it's 300 is 100 plus 200. Altitude just, it just does, right? How could it not? Does that make sense? If you want to see the algebra, here's the algebra, right? But I think that's ultimately unnecessarily tedious, and better to understand it intuitively. Okay. All right, so this thing called change is an accumulating quantity. Okay, what is the associated density? So let me remind y'all of this formula from Chapter 2. I know that's a long time ago at this point, but what we understood from Chapter 2 is that if you have a displacement in your domain, dx, and you want to know how much does the function change correspondingly as your input displaces by dx, you want to know what's the corresponding output change, dot product with the gradient, right? So we didn't even really have to derive this. We already had this formula. How handy. Awkward, not exactly a form I needed in, so I'm going to rewrite dx as TDS. Flashbacks, again, to Chapter 2. Long ago. Oh, wait a second. No, that was, flashbacks to some time ago. And all together, then, we have this formula that tells us output change. You'll notice per unit size in the domain. If you've got a little piece of curve, right, the dx vector tells you your displacement, but ds tells you how big is that little piece of curve. Namely, how long is it? ds represents the length, and length is size. So, accumulating quantity per unit size. That makes this gradient dot t the associated density. That's quantity per unit size. And once you have an accumulating quantity, you know the associated density, you're in business. And here it goes. Change is an accumulating quantity. The whole is the sum of the parts. Right? Over the entire curve. If you want to know how much does a function f change over the entire curve, fine. Break up that curve into little pieces. And on each little piece, look at how much change there is on each little piece. And then add those up. Next, as we wrote above, quantity per unit size is associated by the corresponding density, what I'm going to call change density. Let's see if I can, there we go, here we go. Right, so this blue sort of substitution here, that's exactly what we have in blue here. And again, gradient dot t is our density. And we've basically got a theorem here. The one little thing to sort of fix, I guess you might say, is the notation. We tend to not write the fundamental theorem of line. We tend to not write vector line integrals like this. It's convenient in certain contexts, but I really have a preference for writing it instead like this, keeping in mind that TDS is just dx. How are we doing? Everything's good. All right. Okay, so that said, let's look at this version of the theorem, which frankly is kind of how we tend to think about vector line integrals. This is how that's how I'm going to be writing my vector line integrals. And so reasonable question to ask is, how should I make sense out of this thing? After all, we have an integral gradient, not gradient.t. Gradient is our integrand. How do I think about it? What is the gradient? How does that make sense as an integrand by itself? And so here's where I'm going to come back up to here and kind of revisit this equation. So we were looking at that right there. We use this to make sense out of gradient.t as being our density. Let me talk about density again real quick, just as a reminder. Y'all have heard me say this a million times. We all get taught in middle school that it's mass per unit volume. Okay, all right, but then we have to broaden our sense of what this word density means. It doesn't have to be mass. It can be any accumulating quantity, and it doesn't have to be volume in the denominator. Any sense of size, right? How big is your thing? It is either volume or area or length or whatever appropriate to the context. So here's where we're going to broaden our sense about density a little bit more. Not only can it be any sort of size, volume, area, length, it could even be a vector. It's just a matter of being open-minded. So looking at what we have here, right, I'm going to try to make sense out of dx as being a kind of a size of sorts. I mean, after all, if you think about it, dx is literally a vector whose magnitude is literally the size. So dx is size and more. It's also telling you which direction is this size pointing. You might even say, what is the orientation of that little piece of size? And so with the idea that dx tells you both orientation and size, I'm going to call it an oriented size. So now we have accumulating quantity per unit oriented size. And doesn't it make sense that if we're going to have an oriented notion of size, wouldn't it be reasonable to have this corresponding density be thought of as an oriented notion of density? Now, this is just words, right? But it's not an entirely unreasonable sort of generalization of our idea of a density. And it's going to turn out that this idea of an oriented density is going to be a pretty handy point of view later on when we get into Chapter 7. And so I like to plant the thought here, and then we get to capitalize on it in a couple of weeks. Okay, with that in mind, and now coming back down here to where we were, returning to the question, how do I make sense out of gradient? Well, gradient is my oriented density. It's the density in particular where the quantity in question is change. And so I like the term oriented change density, which in my experience, nobody says but me, right? So why do I push this on you? It's not because I want y'all going around talking about oriented change density, this, that, and the other thing out in public, right? It's because I think there's good ideas in here. So think about how this is an oriented thing. It's telling me about a density of the quantity called change, and so the term kind of makes sense. This is for intuition purposes. It's not for communicating with other people outside of this class. Okay. All right. Yeah, let's do an example. And again, I didn't erase my junk from last time. Okay, so here, an explicit example. Yeah, here we go. Question says to compute a vector line integral. Now, we could have done an example like this at any time in the last few days. It's just a vector line integral. We know the vector field. Parameterization given. Plug and chug. Right? And pull back through the parameterization in all the usual ways. We get everything we need. Why do we need another method, you might say? Now, I'm going to point out, though, that this being parameterized, keep in mind that means that this is your x, and so each one of these x's over here is actually a cosine. It's a little annoying. And this is our y. That means that each one of these y's is actually a sine of t, and so there's actually a bunch of trig inside of that vector field, which is not something we're really looking forward to, right? All else being equal. And then furthermore, keep in mind that this being wrong color. This being our x vector inside of the dx. Keep in mind there's an x prime. That x prime is also going to have sines and cosines. This is actually going to be a bit of an annoying integral to actually have to crank out. All right? So, I guess you could do that, I suppose, but it's not looking like it would be a great calculation. So here's the much better way to do this question. Much better. Just observe that this vector field is a gradient, and you can just directly confirm that using that as the anti-gradient. Right? Take the gradient of x squared y squared, and sure enough, you get that f. So we have been asked here to compute a vector line integral, but again, not a random vector line integral. We've been asked to compute a vector line integral of a gradient. So we can use the fundamental theorem of line integrals here. Yeah?
Can you explain where we got the x squared y squared?
Yeah, that's a good question. I always kind of hope no one's going to call me on that, but you caught me. No, great question. So where did I get this x squared y squared? I'm going to show you how to do that later. There's a process. It's a little bit of a distraction from the ideas we're building on right now. So it's not going to be today. It's going to be Wednesday. But there is totally a method. And for the moment, let me just say I consulted my inner oracle, and that's what right. Okay. All right. Is everybody okay with that? We'll fill in that blank tomorrow. Wednesday. Yeah. Oh, speaking of tomorrow, I'm sorry, y'all. I know I said I was going to make every effort to get the grading done this weekend. I really did try. This just didn't work out. So it is slow going. I should have a bunch of time available tomorrow to hopefully, fingers crossed, get that all done. And of course, I'll email you as soon as I get it done. Okay, so we have a gradient, and it's all over at this point, pretty much. Fundamental theorem of line integrals tells me I can just use that formula, f of b minus f of a. I already have my anti-gradient. The thing whose gradient is my vector field. That's what that f is right there. All I got to figure out now is what are the a and the b. And the a and the b are pretty straightforward observations. So in particular, notice my curve apparently starts when t equals 0. You can take t equals 0, plug it into there, see what comes out, and that's your a. And that's just plugging in. Likewise, you can see that the curve stops when you get to t equals pi, which again, you can plug in, and that turns into that, and that then is your b. So f is given, a and b are easily identified. Plug and chug f of b minus f of a. Your answer is 0. Notice in all of this work, no trig, no half-angle formulas, and right, resulting annoyances. Everybody happy? All right. pretty cool theorem. There is a related idea called path independence, and I'm going to segue into this for dramatic purposes by trying to make the case that this should not be possible. And it really feels like it shouldn't be possible. So first innocent observation, if you're going to compute a line integral, well, it kind of matters what that curve is. Right? Totally different curve, totally different points you're plugging in, totally different values of the vector field. Of course, you're going to get different values of a line integral if you look at a different curve. So again, I hope that's unsurprising. That said, it turns out, amazingly, there are some vector fields called path-independent vector fields. Path-independent vector fields have this feature that when you're looking at line integrals along different curves, you always get the same value for the line integral. And it's just shocking. It's preposterous to think that this could be the case. C1 and C2, different curves. You're plugging in different points to the vector field. You're going to have different values of the field vector here versus different values of the field vector there. How could the integrals always end up being the same? Now, there is a very, very critical asterisk on this. These two curves can't be entirely unrelated. They do have to start at the same point. They do have to end at the same point. But still, I mean, the curves are going to go over totally different paths. This seems highly implausible. So I think it's a healthy starting point to view path independence as an outrageous suggestion that it could even be possible. And now just for fun, just for for dramatic purposes, here is actually I'm going to leave that there. That's kind of convenient. Here's an example of a vector field, 0, x, in the background of this picture here. Notice all the vectors point up. And we've got two curves, the green one and the blue one. They both start at the origin. They both end at 1, 1. Right? And dare I say, obviously, the line integral on the green curve and the line integral on the blue curve are different. Of course they're different. They're different curves. Right? The values that I'm plugging in for the vector field along in here, along this green curve, notice the blue curve doesn't go anywhere near these points. So if the vector field over here matters, then the blue line integral won't even notice those. They shouldn't be the same, and they're not. Again, this is the way it seems like it ought to always be. It ought to really depend which exact specific path are you taking. Now, that said, drama established. Here's how it actually works. That vector fields sometimes actually reasonably can be path independent. Not only are there some path independent vector field, there's a lot of them. There's a whole category of them. And specifically, it is gradients are path independent. Okay, now, how does that work? Well, again, let me set it up. I'm going to give you two curves that both start at A. They both end at B. Here they are. Here's C1. Here's C2. Notice I'm going to be looking at the line integral over C1. I'm going to be looking at the line integral over C2. At a casual glance, we feel like, well, of course, these ought to be different. Again, totally different curves. But notice both of these line integrals are of a gradient. And if you're doing a line integral of a gradient, we have the fundamental theorem of line integrals. The fundamental theorem of line integral says you can evaluate said line integral by looking at f of b minus f of a. So I can evaluate this green line integral only by looking at its endpoints. Right? This green curve, I evaluate it by looking at a and b and using the formula. The blue curve over here, how am I going to evaluate its vector line integral? Well, again, it's integrated as a gradient, so I can evaluate it by looking at the endpoints. And they have the same endpoints. Thus, they have the same f of b minus f of a, and therefore these two integrals being both equal to the same thing are equal to each other. Right? Yeah?
What if like the gradient field looks somewhat like the field in the previous example? Like what if it's independent
Right.
variable?
What we have, that's a great question. What we have is evidence now that there actually is no way that this can be the gradient of anything. And I think that's actually kind of plausible if you think about it. I mean, how could this, what would this look like to be a gradient of something? I mean, uphill is always that way, but it's a lot steeper like this. It's not steep at all over here, but all of these points are on the same altitude, and these points have the same altitude. It doesn't make any sense, but it just doesn't it doesn't make sense. I'll say this: I challenge you to find a hill for which this vector field is the gradient, and you're not going to find one, right? And I've got another, an easier to see example in a couple of pages. Yeah, but short answer to your question, yeah, this cannot possibly be a gradient, and so your question is very reasonable, but the answer is that there's no such cases. Yeah. All right. Anybody else? Everybody all right? All right. Yeah, so every gradient is path independent. Oh, asterisk. We do have to restrict our attention to continuous vector fields. Things get weird. There's all sorts of ugliness, sophisticated, substantial, very problematic issues that come up if you venture outside of nicely regular vector fields and functions. So we're going to assume no singularities, no discontinuities. Everything is just nice, and things are going to go through much better that way. Okay. All right. Now, every gradient is path independent. Harder to show, but also true. Every path independent vector field is also a gradient. Again, with the understanding that we're on, continuous only. Okay. And you don't need to worry about the proof. Okay. All right. Here's a different way to think about it. And again, I need to clean up my mess. Okay. Different way to think about path independence. Let me remind you what our existing way is to think about path independence. Shared starting point, shared ending point. One curve with the appropriate start and end. Second curve, same appropriate start and end. Path independence says that the first integral and the second integral are equal. So this is what path independence means right there. Okay. Now, trivial observation. Green equals blue is equivalent to saying green minus blue is 0. Really nothing happened there. I moved one term to the other side of the equation. This is an identical statement. Right? Okay. Now let's look at this difference. The green integral minus the blue integral. Keep in mind what minus signs do when you're talking about vector line integrals. Minus signs correspond to going backwards along the curve. So I'm going to think of this right here as moving along the curve C1 followed by going backwards along C2. And I can actually draw that curve. That curve starting by doing what C1 does, and then now going backwards along C2. Let me just put some arrows down there like that. All right, so that's my new curve C. And the idea is that curve is just doing sort of, again, C1 followed by backwards along C2. So the suggestion of path independence, namely that green is equal to blue, namely that green minus blue is equal to 0, That is equivalent to saying that this orange line integral is equal to 0. And let's take a closer look at this orange line integral. This orange line integral, you'll notice, starts here at this point A, and then it goes along, and then it goes along, and it starts coming back, and check it out, it ends back at A. It ends at the same point that it started. That means that this orange curve here is a closed curve. And so that gives us another sort of new way to think about, another new way to think about path independence. Alternative statement is that on closed curves, the line integral is equal to 0. Let me say that a little bit differently. Line integral on a closed curve, where have we heard that phrase before? Circulation. So alternative phrasing of path independence is that all circulations are 0. Everybody on board? In some moments, this is actually a really useful point of view, alternative point of view. Okay. All right. Cleaning up the mess again. Right. So let's think about a particular application of this. So I'm going to think about the vector field, which is what I'm going to call steepness. So the gradient of the altitude function, as y'all know, I like to think about altitude and vector field being the gradient of that. So steepness, I think, is a reasonable thing to call it. After all, gradients point uphill, and the magnitude of that gradient tells you literally how steep is that hill. What can I say about this vector field? Well, it's observably a gradient, which means, as we just discussed, it's path independent. Which, as we just discussed, means that all of these closed vector line integrals are all 0. Again, as we just discussed. Now, let me take a particular point of view on this. What am I adding up a bunch of here? Right? Now keep in mind, an integral, you're just adding up a bunch of things. These in green, these are those things. What is f dot dx? Well, our f is a gradient. So gradient dot dx, again, that just tells you the change, how much this function changed, and in particular, how much this altitude changed. Each one of these green summands here is making it's, how much did my altitude changed as I walked along that little piece of my curve. So the integral is the total altitude change. So we have a nice conclusion here. I'm going to call kind of, dare I say, obvious, but this says that when you walk on any closed loop, go out to the hillside somewhere, any closed path, take a hike, start and end at the same point, your total altitude change has to be 0. And again, kind of obvious, right? If you park your car at 5,000 feet altitude, and then you go off on a hike and you do all sorts of things, ups and downs, et cetera, you come back, you end up where your car was, which is still parked at whatever I said, however many thousand feet altitude. You're back to the exact same altitude because you're back to the exact same point. So again, kind of an obvious conclusion, but this is mathematical formulation of it. So what does this do? How does this serve us? Well, nice example is what I like to call Escher stairs. I don't know if you all know the artist M.C. Escher. He did a bunch of drawings, mostly drawings, I think more so than paintings. But one of his common themes is sort of geometric illusions, geometric impossibilities that he can make in the drawing look possible, even though in the real world it's just not at all possible. Right? And this one here with the stairs actually is a lovely example of this result that we've got here, which is ultimately about path independence. So let's look at this person right here. You can see he's going up the stairs. These people that he's following are all going up those stairs. And then they turn and they go up those stairs. and then they turn and they're going up those stairs, and then they turn again and are going up these stairs. And so the suggestion here is that as these guys go around that closed loop, he's drawn it in such a way it makes it look like they've been going uphill the whole time. Thus, it makes it look like their altitude gain line integral would appear to be positive, the way this has been drawn. Right? Not possible. Total altitude gain on a closed loop, of course, has to be 0. So what we have here then is a kind of a mathematical debunking of what's sort of obviously an illusion in this art. Does that make sense to everybody? All right. Moving along. Why is path independence useful? It's actually useful in a couple of ways. One of them is what I'm going to call conceptually. Not everything's about computing stuff, right? So those of you who have had a physics class know that when you're doing mechanics, a very powerful idea is this idea of conservation of energy, right? And so, for example, if you've got something that's sitting up here and it's got a certain amount of altitude and therefore a certain amount of potential energy, if you drop it and maybe it's moving along a track or something and it goes around the track and then it ends up over there by the door at a certain lower altitude, how fast is it going? Well, you don't have to keep track of forces all the way along the track. You can just say, look, it had potential energy up here, it's got kinetic energy correspondingly down there. And this one simple idea saves you tons of trouble on keeping track of what would otherwise be tedious. So where does that idea of potential energy come from? And this is actually a sophisticated question. Why do we have what we call gravitational potential energy? Why do we not have friction potential energy? I don't know if you ever thought about that. There's gravity is a force, so is friction. How come one of them has a corresponding potential energy and the other one doesn't? They asked you a little question, right? So ultimately, depending on how you look at it, I suppose my answer is that path independence, you make certain clever observations, path independence being the key point, and you can show that it makes sense in the context of a path-independent vector field, and it doesn't make sense in the context of a vector field that's not path-independent. So this is, like I say, a very useful conceptual application of path independence. We didn't actually compute anything, but we learned an idea. We created a concept called potential energy. Okay. All right, so it's really, really useful for things like that. Not so much computationally because of the following. I mean, if you think about it, if you have a path-independent vector field, it's a gradient, which means it has an anti-gradient, which means you can use the fundamental theorem of line integrals. Who needs path independence? We've got the fundamental theorem of line integrals, which is a killer. It's awesome, right? So doesn't seem like path independence would be all that useful from a computational point of view. That is mostly true. But notice if you're going to use the fundamental theorem of line integrals, you would need to find that anti-gradient, and it turns out sometimes it's hard to find anti-gradients. Not that much, I suppose, but it can be hard sometimes. So I want to show you how to use path independence as a computational tool just for these circumstances where you can't find the anti-gradient. And here we go. Let's consider let's see here, this vector field given, you'll notice, to be path independent. Now, in the real world, that typically won't be given. So a looming question over this entire example is how would you know in the first place if your vector field is path independent? And that's something that I'm going to show you all later. Probably not going to get to it today. But there is a great answer to that question. For the moment, let's just take it as a given. This is path independent. We have a curve here, top half of the unit circle oriented clockwise. that. There we go. There's our curve, and we want to compute this line integral. Now again, resist the temptation. You look at a line integral like this, and it's tempting to say, okay, well, I'm just going to plug and chug. I'm going to parameterize this curve, pull back through the parameterization. Again, it's going to get ugly because x and y have sines and cosines in them, which means the vector field's going to be chock full of sines and cosines. Nobody wants that. Okay, so, but because my vector field is path independent, as long as I fix the starting point, as long as I fix the ending point, I can switch to any other curve I want. I could use that blue curve if I wanted to. I don't want to, but I could, right? And likewise, if you want to, you could use this curve, whatever. It's all fine. Any curve, as long as it starts at the right point and ends at the right point. All good. What curve are we going to choose? Well, obviously, we're going to choose the curve that makes our lives the easiest. Right? Why wouldn't we? Nice straight line. Easily parameterized if you might want to look at it that way. How are we doing? Is everybody okay? Now, just for emphasis, let me point out, because we have path independence, because I know I'm allowed to switch to this other curve, notice I can now completely scratch off the green curve. I have no further need for that originally given curve. All I needed to know about it was the starting and the ending points, and I've got those, and I've picked my new curve. And now I'm just going to worry about the new curve. Again, you've got a parameterization. You could already call this a victory. Notice, no trig. No sines and cosines. You can imagine plugging this into the vector field. It's totally going to work. It's fine. Right? You can, do all the algebra on that. I like to make a couple of clever observations here. First thing, notice this curve. You can see it right here in this parameterization, but you don't even really need the parameterization. Y is clearly always 0. Right? You look at this curve here. It's entirely on the x-axis. It is immediately, obviously, y equals 0 the whole way. When something like that happens, you're allowed to use that information. So I get to take this y equals 0, plug that in right there, and that makes this whole entry right here 0. Easy. Nice. Here's the next observation. And this is a similar but different observation. For some little piece of curve, let's say this little piece of curve right here. I'm doing in red. I've got my little dx vector that represents displacement along this little piece of curve. Again, geometric appeal. Looking at the curve, it's entirely on the x-axis. It's entirely horizontal. That dx vector, being as it is 100% horizontal, its y component is 0. Because it's not pointing up at all. It's not pointing down at all. It's 100% horizontal. So I've got two different geometric observations that I've made about my new curve. Because y is equal to 0, I get to put a 0 there. Because my dx vector is horizontal, I get to put a 0 there. Oh, we're done. This dot product's immediately 0. Game over. Not only do I not have to do any trig, I don't even have to do any real other algebra either. Everybody okay with that? Pretty cool move. Okay. Now, I didn't want this example, when I was writing this example, I didn't want the algebra to get out of hand, so I picked a vector field that is, not that hard. And being as it is not that hard, it's also not that hard to find the anti-gradient. And I'll bet you y'all could eyeball this, kind of think strategically, and come up with an anti-gradient without too much trouble. Use the fundamental theorem of line integrals. Fine, you could totally do that. That said, there are examples of vector fields that are really ugly looking, for which finding the anti-gradient is hard. But making a path independence argument can still be easy. And if you hunt through my old midterm exams from 10 years ago or whatever, you'll see some examples where I created some such questions. Okay. And this is a pretty good place to end it. I'm pretty sure we're out of time, so we'll call it a day there. And y'all have a good one. See what's going on here. Yeah. See you later.